Good morning, ladies and gentlemen. It is my pleasure to introduce Dr. John Bristow this morning. John completed his undergraduate studies in geology and an MSc in geology at the University of Natal in 1976 and a PhD in geochemistry at the University of Cape Town in 1981. His subject was the geology and origin of the Karoo volcanics preserved in the Lebombo monocline, which stretches down the eastern margin of South Africa. Thereafter, he spent 2 years on a postdoctoral study of volcanic deposits and processes in the western United States, based at the University of New Mexico in Albuquerque. John subsequently pursued a successful career in the local and international minerals exploration and mining industry, primarily in the diamond sector, initially with De Beers, and thereupon in his own business and in junior mining ventures. He now resides in Hermanus with his wife Marilyn, where he and his colleagues of the Overberg Geoscientists Group are spending time highlighting the remarkable geology and its related features, including climate change, of the Overberg region here in the Western Cape. The emphasis of the Overberg Geoscientists Group is on taking geology to the people, primarily the youth, in the interest of fostering young talent and geologists of the future. As you may know, ladies and gentlemen, the United Nations declared this year the International Year of Glass. And we've presented various lectures on the subject. And since silica is one of the base minerals required in the manufacture of glass, John prepared this lecture. John, thank you very much, and we're really looking forward to your presentation.
Thanks, Gert, and good morning, everyone, ladies and gentlemen. Thanks for making the time to attend this presentation. And thanks to Gert and his U3A team for the excellent programs they put on for U3A. It's been a real pleasure to work with U3A in the course of the last few years. We work closely with them, as this presentation will show today. Just by way of background, I think many people will probably be aware that this year has been declared the Year of Glass. This extremely important mineral product that we use so extensively in our daily lives, from the windows that we look out of our houses, screens for computers and smartphones, and all the other applications that come with it. So today I'm going to do a general presentation on glass stroke silica. Obviously, the key component of glass is good quality silica. And with that silica, we can then go forth and prepare and produce tons and tons of glass, which, as I said a bit earlier, impacts our daily lives, and we'd really struggle without it. So this talk is going to focus on sort of the general background of silica, but being the main component of glass. I'm going to show, an overview of all the many forms of silica, where it comes from, where it's mined, and so forth. And I should also just point out that next week there will be a very interesting presentation by Stephen Davey, who's again a very smart geologist. He does a lot of work in organizing people's permits for mining quarries and sand and aggregate in the Western Cape here. He lives in Darling, and he will give a presentation focusing on the Cape Flats, which particularly an area called Philippi, which some of you will know produces really high quality silica sand, which is then used for making plate glass, float glass, and other glass products. So without further ado, let's get on to the presentation. Just a pretty picture here of very fine silica needles in this mineral specimen, just to show again a bit of the variability of this amazing mineral called silica or quartz, SiO2, and so forth. Just in terms of structure of the presentation, there are sort of 9 loose divisions in this presentation, from earth structure and silica and where we find silica in the crust, properties of silica, forms of silica, its many uses, where do we find silica deposits that we can mine, silica health challenges, interestingly, cosmetic uses. And then the unsustainable situation that we're seeing around the world, unsustainable situation of sand and gravel or aggregate mining, and then the importance of recycling, and then the end. And if we have time, we can take a few questions and answers. And very simply, the 3 slides images on the right-hand side show the typical sort of sequence I'm going to talk to. So we have beach sand and dune sands and sands like this with ripple marks on them. That's the sort of starting product. And of course, the higher the grade, the cleaner the sand, the better. In the second slide, we have typical mining operation. We don't realize how much sand is actually mined in the world today. And this whole topic, industrial minerals, is I have found very fascinating, because we hear a great deal about, you know, the big mining companies like Rio and BHP and Anglo American and the gold companies, but we forget that there's also a number of very serious mining companies around the world who focus on these non-sexy minerals, as in sand for silica, clay, and industrial minerals in general. And then obviously the third point there, third slide, is just a snapshot of silica fiber that we now use around the world to communicate with one another, transmit information at very high speed. So, you know, you go from the raw silica sand at the top to this highly refined strands of silica product as in these fiber optics cables, which allows us to communicate at great speed across the world. And where does most of our silica sit, and where does it come from? And I'm going to use the terminology a bit loosely here. So we have, you know, pure silica Si. We have silica dioxide, SiO2, which is effectively, we loosely refer to as quartz. And so if I use the terminology a bit loosely, forget me. Looking at the cross structure of the Earth, which I think most of us geologists will know, we have a thick molten core and mantle, upper mantle, and asthenosphere, and then floating on the top of this round molten Earth of ours, or molten in the middle, hot and plastic higher up, and then rigid and cold on the crust. And that crust, I guess, on average, is about 100 kilometers thick. So it's a very thin layer that sort of skates around, a thin rigid layer that skates around on the underlying hotter and more mobile parts of the mantle and deep core. And under mountain chains, obviously that thickness of the crust gets a bit thicker. Out in the oceans, in the mid-ocean ridges, and that the crust, so to speak, is rather thinner. So that's just the general setting where most of our silica resides. If we go and look at the composition of the Earth's crust, this is quite an interesting diagram. We'll see there that oxygen, silicon, aluminium, and iron comprise about 88% of the mass of the Earth's crust. Silicon, Si, comprises about 28.2% of the Earth's crust. Obviously, it's tied up in different forms, and quartz itself, SiO2, equates to about 10% of the mass. So those minerals on that chart on the right-hand side are our sort of most common rock-forming elements and minerals, and we find them in quite significant abundance. And the important thing to note in all of this, of course, is that there are another 90 elements out there that comprise the remaining about 12% of the elements that make up the rest of the crust. And quite critically, and this is an important one for miners and explorers, is that if you take the minerals that we typically mine in great abundance, gold, silver, copper, base metals, those are collectively, they comprise less than 0.03% of the crust by mass. And there's a lesson in there which says that, you know, when we come to the situation where we're starting to mine more of these base metals like copper, and equally cobalt, lithium, rare earths, we are now starting to mine very rare commodities, and many of them, diamonds being a good example. Obviously, you start looking at the sort of parts per million and parts per billion type situation in terms of the abundance, and you've got to move a great deal of rock or whatever the case may be to extract those minerals. So let's not kid ourselves. When it comes to producing all these green minerals or critical minerals that we need to make our environment cleaner, we're certainly not going to see less mining. We're probably going to see more. If we move on to Silica Properties, it's a very interesting and important mineral for a number of reasons. One of them, obviously, is the fact that it's transparent. It makes nice, clean, glass that we can see through with ease. And there are lots of things that we can do with glass. It has a density that is both, relatively high, but it's not that heavy, which again is important, because if you're going to use plate glass and this glass all over big buildings, modern buildings, many now will have almost whole structures of glass supported in steel and aluminium. You don't want a mineral that becomes so heavy that you can't support it up there. The melting point is high, but it's not not too high. You can still melt it. You can make plate glass or float glass effectively by putting silica, clean silica, into a big furnace, heating it up, and then pouring it over the bars of tin. So you roll it out over molten bars of tin, and that's the way that float glass is made. So it's a very useful, very robust mineral. It's not too heavy. It melts at a high temperature, but you can melt it, and you can do lots of things with that. If we go and look at the geology, most silica SiO2 is most commonly found as quartz, and that comprises, as I said, 10% biomass of the Earth's crust. There are various forms of silica, particularly polymorphs. Quartz per se is the only one stable at the Earth's surface, but we do find other metastable types of quartz, cosite and stishovite being two, around impact structures, for example. And we find other high temperature forms such as tridymite and cristobalite from silica-rich volcanic rocks, and we'll talk a little bit about that in the next slide or two. The other important thing is we don't realize that silica actually occurs in many plants, many of our foodstuffs for that matter. The classic one being plants such as rice. And rice, when you go chewing it and cooking it, you end up digesting a fair amount of silica. And of course, there are many other plants that grazing animals eat, or the ungulates. And that those plants also have a fair amount of silica in them, and that helps their digestive systems. Obviously, the downside of that, it also causes tooth wear. So that high levels of silica in plants are frequently eaten by the herbivores, and many of them have developed silica in their structure, probably as a mechanism against predation. Silica or rice husk ash is also very useful stuff, in that it gets used in filtration systems to make cement and concrete. And then the other thing that also occurs in nature is silification in and by cells. And it's not my expertise, we're not going to go into it, but many of these remarkable fine structures that we found in the ocean, for example, diatoms, radiolaria, spicules, and the structure of sponges, the skeletons, consist of basically silica. Okay, let's start moving on to the various forms of silica. Typically, we have well-known crystalline forms of silica, which are ubiquitous in nature. If you just look down at the bottom of that slide, quartz crystals, very common. Most of us have got a specimen sitting somewhere, and then we'll get things like, very colorful tangerine quartz. And these minerals and elements become the building blocks of most of the rocks that we see at the Earth's surface. Here in Hermanus, where we live, we've obviously got an abundance of Table Mountain sandstones, and they comprise this amazing Cape fold belt that we see all around us, and are very extensive on our west coast and here along the southeast coast of the Cape and all the way up to KZN. The other side of the other forms of silica are the effectively amorphous silicas, for example, opal being a good example, which is a hydrated amorphous form of silica. So it's SiO2 with some water tacked onto it. And typically a good example of it will be the opals that are mined from sort of vugs and veins in places like Australia and drive small sort of semi-precious industries. Silica glass, fascinating stuff. Obsidian, commonly found around silicic volcanoes. These glass flows flow and then they solidify and form amazing features. And certainly in the Western US, the Navajo Indians and other indigenous people in other parts of the world as well have found obsidian very useful in terms of making spearheads or arrowheads for hunting wild animals. And if you go back into archaeological digs and that, you'll find these fascinating tools in places in America, and we even see some of them in Southern Africa, I guess, where we've had either silicic volcanic activity or we've had sort of pure silica which have been used to make digging instruments and other hand instruments. Interestingly, in that picture on the left-hand side of the obsidian glass is not particularly stable at the Earth's surface. And the sort of white flowery spots that you see in there are what we call devitrification. So the glass is starting to effectively devitrify or crystallize, and those will be sort of little flowers of cristobalite forming in the silica glass. Looking at color forms, we have some amazing colors. Rose quartz, typically due to trace amounts of titanium iron or manganese, gives you the pretty rose hues. And then the other interesting one is effectively the blue agate, and in particular blue lace agate. It's quite rare. I think the best known and one of the few sort of classic deposits of blue lace agate is in southern Namibia. There's been a lot of good work done and written up by Duncan Miller on blue lace agate. And very interestingly, the color of blue lace agate is caused by Rayleigh scattering, and it's no different to, why is the sky blue? Well, the way light is passed and refracted through our atmosphere to give it the bright blue color, particularly if you live on the high veld on a good day. It's the same sort of process that gives us the blue of blue lace agate. And moving on, these will all be sort of classic specimens or examples of specimens known to most geologists. Amethyst, the purple silica, clear crystalline quartz is obviously quite common around the world, and good specimens still fetch decent prices. Down on the bottom left, we have smoky quartz. Smoky quartz is due, or the sort of brown color, excuse me, of smoky quartz is due to aluminium in the lattice of the silica, and that aluminium with the color, with light rays moving through the silica gives you this sort of pretty brown hue, and we see a sort of more filamental growth of silica on the left-hand side, and again a smoky quartz growth. Just if we move on to the many uses and applications of silica, the list is vast. I always knew there were lots of applications for glass, silica, but when I started looking a bit more and doing the research for this presentation, it came home to me just how many applications and uses there are for good old Si2, silica, and obviously, read glass. So construction materials, aggregate, sand, cement, ceramics, all the ones that we sort of know of and take for granted every day. Glass itself, the more important part, and that's really the focus of this presentation. There are literally thousands of uses and applications for glass, starting with float or plate glass for windows, sheet glass, laminated safety glass. You can go on and on, laboratory wear, bottles, eyeglasses, which most of us more senior people wear today, optical systems, mirrors and prisms. Then we move into chemically strengthened glass. The fact that glass is inherently inert and it's quite robust. It really takes a very strong hydrofluoric acid to etch and dissolve glass, but for most parts, glass windows really stand up very well against the elements. But if we look at the strengthened glasses, we'll all know or heard the word or talk of Corning glass. Very, very robust, very, very strong. You can pour boiling water into it, put it on a cold surface, and it won't shatter. Then the other increasing use of flexible glass is obviously all about fiber optic cable. I showed you a picture right at the start of fiber optics in a cable. It's extremely pure glass with very few defects for obvious reasons. If we want to transmit data quickly over vast distances, you don't want anything interfering in that glass. Corning have again been the sort of key company who introduced willow glass in 2002. It's a flexible glass based on borosilicon glass, and then other companies followed suit. And down the bottom, you'll see again just a couple of names that are familiar, Pyrex and so on, which are really all forms of borosilicate glass. And obviously there we move into solar cells, huge application and growth these days of solar panels for taking us off the grid, which I think we're all trying to do here in South Africa. So solar panel glass, semiconductors for computer microchips, fiberglass and glass wool. As I said, the applications run into effectively thousands. When we look at glass making, this obviously important process, glass making dates back to at least 6,000 years, long before humans even discovered how to smelt iron. And archaeological evidence suggests that the synthetic glass at that time was the first, synthetic glass was made in Lebanon and coastal areas of North Syria, Mesopotamia, and ancient Egypt. Again, I've always found fascinating the artwork in windows, colored windows that we see in many churches and cathedrals. Aside from the sheer artwork that's gone into that, the coloration or the colors are fascinating, and this again goes back hundreds of years. So this is a picture of the Basilica of Saint Denis near Paris. Some of you have probably been there. One of the earliest uses and examples of extensive colored glass, and this stretches back to the early 13th century architecture, which restored glass from back in the 19th century. So we're talking really old periods here where people were already using glass extensively in buildings. If we just then move on to the way we use glass and silica in our daily lives, this very busy diagram shows glass use or silica use, and again use of lots of other minerals that we rely on daily to keep the world ticking and keep ourselves and motor cars and so on. And if you pull out the silica component of what we use on a daily and yearly basis, stats, and these are from both the UN and the US Geological Survey, United States Geological Survey, we individuals end up using about 6,500 kilograms, 6.5 tons of glass per annum. So it's not an insignificant use of silica sand, silica. If we look at the situation in our houses and homes and garages and vehicles, again, there's a whole lot of red rings there which highlight where we use silica sand, gravel, aggregate, and concrete, right from the foundation all the way through to it's missing in this case the solar panels that many of us now have installed on our homes. So a huge range of uses of silica, and I'm talking now somewhat more about silica, but in all of these structures, obviously glass is a key component for mirrors and windows and TV screens, cell phones, you name it. Windows on vehicles, glasses is there. Then we move into the big trends, follow Elon Musk, hybrid vehicles. Well, hybrid vehicles again use a large amount of silica for particularly glass, but then again a host of other minerals and important minerals, and particularly rare minerals, things like lithium for obviously batteries, neodymium magnets for these super efficient electric motors, and so on. And again, it comes back to my early point that we have to mine all these things. They're extremely rare, and we have to move lots of dirt to actually extract these scarce minerals. Just to sort of wrap up here, again, just following the earlier slides, the many uses of silica or silica glass or glass. In the left top, you'll see the big glass panels on a modern building in the UK. In many cases, you'll use double glazing for cold and heat efficiency. And so the amount of glass, aluminium support, steel structures used in building today is extensive. Solar panels, your Corningware or smart tea set that your grandmother had on the right-hand side with its glazes, and on the bottom left-hand side, optical glass in our lenses so that we can see what we're reading on the screen, computer chips, and then another very big use for glass across the world is obviously in bunkers and preparing greens on golf courses. And that alone is, when you look at some of the figures, and I don't have reliable figures, but the amount of silica sand, clean silica sand that is going into golf courses around the world is again substantial. And then just to wrap up this, just to look at it on a again person base, and this was data from a couple of sources, international sources published by Reuters. Again, interestingly, the figures correspond with the previous one. So we end up using individuals about 18 kilograms per person per day, including in our toothpaste, and we'll come to that. And that equates back to the sort of 6.5 tons, 6,500 kilograms per person. Just as an extension to the use of sand, and obviously there's a great deal of sand, silica sand, clean sand that goes into cement and aggregate and building buildings. This is again a very interesting bit of information that I picked up in the research. If you look at China, most of us will be well aware of the development and the building of cities that's happened in China in the last 20 years, and in fact quite recently. But if you look at what China has used in 10 years from 2006 to 2016, they have used enough cement, so cement stroke silica, to cover more than 90% of the country's surface area with a one meter thick layer of cement. And I'm just using this as a proxy to also say they will have then also used a huge amount of silica sand or sand and aggregate. And if you go and look at comparison of what's been used in the US in the past 115 years, orders of magnitude more than China in terms of the time period, China, the US in all that period of time, 150 years, has only used about a quarter or a third of the amount of cement that China has used. And it just highlights the massive growth that this command structure, so-called socialist system has developed in a very short period of time. And for scale, down there is a replica on scale of the famous Great Pyramid of Giza, which we all, walk around and think is amazingly big. Well, it is, but, it pales into insignificance when you look at the amount of aggregate and sand and cement that's been made in modernizing China. Okay, let's move on. Where do we find and mine silica? Well, dune sand along our coast is a big provider and a big source of good, clean silica sand. And very interestingly, in this diagram, you'll see up on the northeast Queensland coast of Australia, at a locality called Cape Flattery, north of Cairns and Townsville. There's a couple of big silica mines, one of which is owned by Mitsubishi Corporation. Now, I always thought that Mitsubishi was a key sort of industrial company. It made motor cars and things like Pajeros and so on. But when you started getting into the research again, I suddenly found that Mitsubishi produces mines and produces and ships about 3 million tons of silica sand every year from the Cape Flattery mine across in Australia. And if you look at their sort of overall, the structure of their business units, you'll see their industrial minerals and mineral resources are very big in the life of Mitsubishi, which when you drill down also produces solar panels and material for cleaning water, filtration of water, and they're involved in many other applications, infrastructure applications, where silica sand becomes a key component in lots of the things they do. So this is a picture of the sand that's been accumulated at this Cape Flattery mine, ready for shipping. You'll see these big stackers building these heaps from a conveyor belt system coming from the mines and the cleaning plant. The interesting thing about this silica is just how clean and pure it is. And it really is wonderfully clean and almost ready to go straight into the glass making process. So if you look at SiO2 in that table on the top right hand side, 99.93% SiO2 with extremely low impurities of iron, Fe2O3, aluminium oxide, and titanium oxide, and that stuff is as they say, worth gold, given the fact that it is so clean, and you can almost take it from mine to glass making. These are just images again of the shipping arrangements to move this 3 million tons. There are also other companies that mine sand in the area and ship them off to other parts of the world. But most of the sand here that Mitsubishi mines will go to Japan and Southeast Asia. Okay, again, very interestingly, when you look around the world, there's some really big, large, diverse mining companies out there that we don't typically hear mention of in the sort of world mining space. So most of us, miners will be used to base metal companies and gold companies, obviously the Rio Tintos, BHP Billitons, Anglo American, maybe Newmont Gold, Barrick Gold, or typically, the mining companies we're aware of and sort of talk of, but not too many of us will have heard of Imris, which is a French-based company, a very large company. It competes, in terms of market cap, and that would be up with the biggest. And it's all about mining and producing specialty industrial minerals. And some of their biggest product is quartz, silica, and clays. And we don't realize, again, just how large this whole process of mining, the non-sexy minerals like silica, clays, and so forth, how big it is out there in the world, given the fact that, we need lots of it. And if you look at there, what they call performance minerals down the bottom there, ceramics, cosmetics, and personal care, energy, environment, energy, obviously solar panels, they use it in preparing food and beverages. There's health and pharmaceutical applications of silica. It gets used in paints and coatings, obviously big uses in paper and boarding, plastics, rubber, all of those make use of silica for various reasons. Okay, so that's Imris, French-based. They have mining operations in numerous countries. Just two examples there show quarries, sand quarries, silica quarries in France and Sweden. If we move on again, still in Europe, this is Sibelco, which again is a very big industrial minerals company. It was founded in 1872, initially supplying silica sand from deposits in Flanders to Belgium's glass producers. If you go back in the history of Belgium, it was a very big producer of sort of specialty glass, colored glass products, way back in the sort of late 1800s, early 1900s. And some interesting historical pictures on the right there showing old-time mining of deposits in Flanders, and down below you'll see them also extracting sand from quarries which are flooded, which happens quite commonly. And interestingly, that company, Sibelco, you'll see there operates 118 production sites in 31 countries. So it's not a small Mickey Mouse company. With a team of over 5,000 people. So, a big mining venture, but not one you hear of every day, as we would hear, for example, of BHP or Rio Tinto. Just coming close to home, and I'm not going to steal Stephen Davies' thunder. This is a very interesting picture and got some worrying aspects of it on it as well too. This is in the Cape, False Bay. You'll see there just lapping onto the sand dunes down in the south. These are the Macassar dune field in the northeast part of False Bay, immediately west of Somerset West. And you'll see there that 2 is the N2. That's the road that goes from, well, it goes all the way to excuse me, the Eastern Cape. It goes from Somerset West through to Cape Town, Somerset West on the right, the east, and Cape Town across on the left. Anyway, and the dunes there, very interestingly, follow the southeaster. So those dunes, which are trending more or less northwest, have been built over millions of years by the action of the southeasters, which, as everyone knows, blow for many months and quite hard at times here in the western and southwestern Cape. So I just, for interest, went and took some pictures of these dunes, and we'll get to that. And in the process, you also realize the amount of sort of unstoppable development of informal settlements on the left-hand side, particularly of that road that you see. You've got still quite well-preserved dunes to the southeast, and these growing informal settlements on the Cape Flats, in this case sort of Mitchell's Plain. And Stephen's going to talk a lot more about the Cape Flats and show some images that go back about 84 years when this area was almost undeveloped. So the change that's taken place here in effectively a person's lifetime is quite stark and something we should take note of. Okay, so this is a close-up, still a Google image, Google Earth, and I've just blown it up, and you can see these quarries and mining activities. You can see the benches showing there. The red star there in the top right is where I stood to take pictures, or where I stood to take pictures, not this one, obviously this is a satellite image. But if we look at this one, you can see here that the scale the mining taking place in these Macassar dunes. So this is an image looking effectively sort of southeast into False Bay, which is behind the dune structures there. And you can see the extent of the benching on these mining faces. And in the middle there, or middle right, you'll see, and there are a couple of them in the pit, they don't all show that well, a number of big in-pit screens that are being used to effectively mine. So they mine the material, take it to the in-pit screens, screen it into different size fractions. But the extent of mining here is huge, and it's not going to stop in a hurry given the sort of influx of people on an ongoing basis to the Western Cape, and the need for building roads and structures, and it just carries on. Okay, let's move along to look at some of the other aspects of silica, and again, all of this in a sense relates to glass. But if we have to mine silica to produce glass and also recover other minerals and elements, we end up with a problem, if you're not careful, of silicosis. And I think most of us who've grown up in South Africa or been involved in the mining industry are well versed in some of the legacy issues that we have in our mining industry, one of them obviously being silicosis. So Wits gold mines in particular, deep level mines, certainly in the early years of mining, and I guess back then people didn't quite understand the consequences of silica and the fine dust that was always floating around in these mines. And particularly in the early days, drilling and blasting, you never cleared the stopes. You all went and hid around the corner behind or out of the way of the blasts, not appreciating that every time you did a blast, there was a tremendous amount of very fine micro sort of granular dust that would have been produced and blew down these stopes and developments and hallways and got into people's lungs. And again, in the very early years, there would be lots of drilling on the face. Typically in those days, you had to clean the hole before you loaded it with explosives, and you would blow it out with a air hose, blast it out. Once silicosis started to be recognized, we saw the introduction of a lot more water to clean stopes and clean holes, so you had less of silica floating around. Again, most of you or some of you will have noted in 2019 there was a class action suit finally completed, and the mining companies held account for silicosis, have put at this stage an amount of money of 5 billion rand aside for treating old miners with silicosis. Also trying to track them down in fairly remote areas. Many of the older miners, of course, went back to or migrant miners would have gone back to their homes, either in South Africa, Lesotho, Malawi, Mozambique. Tracking these people with silicosis is quite challenging, and it's a problem that's not going to go away. And certainly, I think there are a couple of NGOs that have been set up to try and track down people and ensure that they get treatment for silicosis. And it's not a nice disease to have. It effectively destroys your lungs, and I guess eventually, a bit like we saw with some of the extreme forms of COVID, you end up not being able to breathe and end up dying. And I guess there's a lesson here that being aware of occupational health and safety aspects, silicosis obviously one of them, and other pollutive type situations. I mean, many people will be aware that in the anarchy or the riots that we had in July 2021 in KZN, there was a chemical storage facility that burnt down in Durban North, and that facility again released really obnoxious dangerous chemical gases. I think there was spillage of some of these chemicals that got into the water table, or certainly the drainages. And I see that one of the sort of catchment dams that was built to contain some of this poisonous material was breached recently in the big floods they had at KZN. And it just begs the question, you know, why in this modern day, where we supposedly have good legislation, for example, NEMA, the National Environmental Management Act, we don't have proper policing, and a company like this was allowed to sort of set up in a residential area and house, you know, rather unpleasant and dangerous chemicals. If we move on to medical and cosmetic applications, I'm not an expert in this area by any means, but there are quite extensive uses of silica in bone repairing devices, for example. You know, the good thing about silica, it's inert, so you can put it, I guess, like titanium that they use in hip joints and knee joints and so on. You can put it into people's bodies and your body doesn't sort of immediately reject it. It also gets used in a fine micro form for drug delivery. You know, many of the drugs, particularly cancer drugs and that they use in your body, you need something to deliver or transfer those drugs in your body, and you then need to make sure that it's an inert type of substance. The other form of delivery mechanisms too is to use extremely fine diamonds, which, you know, as we know, are extremely inert. And then good old silica gets used extensively in toothpaste. I don't know how many of us realize that, but if you want nice shiny white teeth, there's a lot more to it than just you know, making a nice tasting toothpaste. You actually need something in there that's abrasive. So good old silica becomes a very useful component of your day-to-day toothpaste. And abrasives, interestingly, were used in toothpaste dating back to over 2,000 years ago, where paste mixtures at that stage were once made with bones and ground shells. And you would then sort of make a mushy, and some of you have done it if you're camping and don't have toothpaste and you want to clean your teeth, you make a sort of nice muddy patch and some fine sand and rub it on your teeth, and it works quite well. Okay, let's move on, and we're coming towards the end now, just looking at worldwide sand and gravel mining, whether we want silica glass or glass, or whether we want solar panels. We need to mine material like silica sand or silica. If we look at here in South Africa, certainly here in the Cape, we have some exceptionally good quality silica in the dunes and in the Philippi area, which Stephen is going to talk about. Up in Gauteng, certainly the Magaliesberg quartzites and places are mined, crushed, washed to produce clean silica. There's a big industry of silica production in Gauteng, obviously for foundries, certainly in the platinum industry. There's a big need for silica, which is used in foundries, for example, and other chemical applications. So around the world, what we're starting to see is that there's a huge use of sand, gravel, and crushed stone. The majority of that would be, you know, siliceous material. Obviously, down here, our Cape environment has naturally produced silica in the dunes, and Gauteng, you're going to mill the Magaliesberg quartzites to produce the same sort of stuff. And you'll see there the sand, gravel, and crushed rock that's used and projected for use into the year 2060 is substantial. And it's becoming, or the situation is becoming unsustainable if you look at the growth of the population and the need for new buildings around the world. And the important thing to note there in the first bullet is for each ton of cement or concrete used, the building industry needs about 6 to 7 times more tons of sand. So there's a, you can't make cement that works without having a great deal of sand and aggregate in that cement. So more and more as we build, more and more we find that we're running out of sort of normal, easy accessible sand and aggregate for this huge population growth of ours. And there in that slide are again the lists or the other uses of aggregate around the world. I mean, obviously asphalt, road pavements, cement is used very extensively for certainly creating the solid base. And then other sectors like glass and electronics and aeronautics, the use is climbing, it's not decreasing. Land reclamation, we're all aware, as we sort of run out of easily accessible land around, many countries, Japan being an example, you reclaim land, and to do that you again need lots of sand and aggregate shoreline developments. Nowadays, if we really worried about climate change, you're obviously going to build walls to keep rising sea level back. So there's numerous applications and uses for sand and gravel. And the important thing, as I say, is if you look at the slide on the right hand side, which is a bit busy, that growth in the demand for sand, gravel, and crushed rock aggregate is growing substantially, and probably in the real world not sustainable. Part of the reason being is that good quality sand, be it or even bad quality sand for that matter, doesn't just form overnight. In our case, we do here in the Cape have big sand dunes that you can mine, but in other parts of the world you have to crush and clean aggregate. And what we're seeing is if these trends carry on and we don't change our lifestyles, the extraction rate is basically much greater than the rate of renewal. I mean, geological processes are ongoing. There is, sand forming on our modern beaches, but that process is a geological process, and it's actually quite slow. And so if we keep on, mining and building at the rate we do, well, we're going to run out of easy accessible sand. And then it gets back to the point that we tend to sort of shy away from. We're going to have to do more mining to find the products that we need to keep on building buildings to maintain the lifestyle that we have. Just for interest, looking around the world, it's quite interesting to see what certain countries are doing to start addressing this sort of unsustainable trend. And very interestingly, and I think many people on here in the audience will probably be aware of that. And if you take a country like Britain, they have very strict rules about knocking down old buildings or old houses or historical buildings that have been there for a long time. You might be able to get approval to modernize the inside, but they don't let you sort of readily just knock down a house in the country, or even for that matter houses in the cities, because again there's a huge amount of effort and cost and gone into that building. So recycling has to become more common and used more extensively. Whether it be plastic, it's no different. It's the same really issue that we should be addressing in terms of our building structures. And there's no reason, given the technology we have today that we use in, say, mining and crushing rock, that all of this debris that we produce when a house or a big high-rise or old power station cooling towers get knocked down, all of that stuff, or most of it, should certainly be recycled, recrushed, and used again. And the sort of images you see on the right-hand side in South Africa, typically what happens to that situation is it all gets picked up and put in the landfill, And those landfalls in this country, many of them are effectively already full, and they don't have much room for left to take up this sort of waste of material that we simply throw away. So recycling has to be much more important as we go forward, and certainly in this country we best start taking note of it. Okay, then just to wrap up and put a few sort of comments and ideas out there, and it goes back to this magic word, you know, sustainability. If we're really serious about it, you know, we need to start making some tough decisions. Obviously, probably one of the key decisions in all of this revolves around the change of lifestyle. You know, we live in this throwaway society where we don't think twice about throwing bottles, you know, into the tip or into the rubbish bin, and they get carted away and thrown in the landfill. I think some of the wine producing companies, for example, here in the Cape, are reprocessing wine bottles more and more, but certainly if you look around and look at our tip, for example, even here in Hermanus, and things work pretty well here, you still see an enormous amount of material that should be recycled going into the local tips and into the landfill. And we don't have a lot of areas to build landfills easily here in the Western Cape. Okay, so, you know, can we change our lifestyle and start addressing it? And I guess that relates to my second point, which is consumer behavior. You know, how do we change habits? Is that possible? Recycling, we've talked about. We see legislation in the UK driving the process, certainly something we should be thinking about here. But in all of this, it all goes back, I think, certainly to education and information. How do we educate people, laypersons, kids, about the importance of, you know, looking after water, looking after our sand, recycling, and particularly amongst the underprivileged and poor communities, you know, who are basically looking to survive every day, and they don't really have time to go and, you know, worry about where you throw a bottle or whatever the case may be. Related to that, obviously, just respect for our environment, and whether that's sand, water, you know, our indigenous vegetation. I think South Africans in general are very poor about that. And the important thing there, all of these issues, it's not really about today, well, it is, but it's more important about 20 and 40 years hence. If we keep on with the population growth that we have, and we don't start addressing some of these issues today, the consequences, you know, down the road in 20 and 40 years time are going to be quite significant. And I'm not looking to be a doomsayer, but I certainly think we should be having a good look at this and looking at these situations and starting to do something. A pet topic of mine, and it'd be interesting to see if Stephen Davey comments about it as well. He and I have had a number of discussions about why every municipality should have a geologist and probably also a hydrogeologist in their employ. We're doing things and building buildings and allowing people to develop on floodplains or develop housing. And then, of course, shock horror every time there's a flood or a extreme weather system like we've just had in Durban a couple of weeks ago. We all glibly, or the politicians glibly, blame climate change. Well, you know, fact of the matter is we people may be exacerbating climate change a little, but climate change is a cyclical thing. It's happened regularly over millions of years, and it's going to happen again. Glacial periods and interglacial periods, we can see it very well documented in the geological record. And it's very interesting if we take note of the Durban disaster, as I call it, recently, where I think we still don't know the final numbers. Over 500 people were killed, sadly, washed away, many of them. That whole situation, and there's some very good articles published about it by well-informed people and good geologists. was really an accident waiting to happen. And the key thing is that no one took note of the basic geological properties and conditions that exist in the bluff and in the bluff sandstones, the Berea red sands, and that whole coastal strip of Durban is geologically an unstable area. And I remember having graduated or done my undergrad work in KZN, or in those days University of Natal, Durban, attending lectures by people like Rodney Maud, who is a well-known, or was certainly a very well-known geotechnical geologist, and spent most of his career in Natal, helping people design roads and where buildings could be done, and foundation work and so on, telling us very clearly back then that the Berea sands or Berea red sands were not particularly stable, and if you allowed them to get wet and slushy, they had a habit of moving from under your feet. So hence my reason of saying that every municipality nowadays, given the people pressure, should have a geologist and a hydrogeologist, and knowledge of their underlying geology, whether it's wet or whether it's going to be slushy sand. When it gets wet, it becomes unstable, or whether it's stable, and again, why you shouldn't be allowing people to develop housing, and typically it's low-cost housing for the poor on areas below the flood line. So that's my bit for the day on effectively glass stroke silica, this fascinating mineral, which is an important part of our geological makeup around this country, and just a very important mineral, and a somewhat neglected mineral. So thanks to the U3A group and Gert for organizing this presentation. And I'll leave it at that, Gert. Thanks very much.
Thanks, John. Talking about recycling, surely the mine dumps, particularly around gold mines, can be recycled, and once they're cleaned, the sand be used for silica. Is that so?
Absolutely, Gert. I mean, I think you spent a lot of your career in Johannesburg, and although you're an engineer, you ended up at the SABC for a long time. And I certainly remember in my youth, many years ago, going to visit family in Johannesburg. Excuse me, you drive past rows and rows of dumps, particularly around old mine dumps, particularly around the southern edge of Johannesburg. And most of those dumps today have disappeared. They were reprocessed, primarily, so to speak, for the gold still contained within them. And over the years, the technology to recover gold has become better and better and more sophisticated. So they were reprocessed, and in the process, a lot of the sand that was produced, and of course the other element or mineral that was also extracted would have been uranium. But the byproduct then was sand, and a lot of that sand has been used in building, particularly, as Johannesburg sort of spread to the north. So yes, you're absolutely right. Obviously, there is still a big dump, and you'll see it if you take off from OR Tambo Airport and fly down to Durban. There's a big tailings dump of clean sand. Some of it is still being used as building sand out on the East Rand. It's not that obvious from the road, or for example, the N3 to Natal. But there is still a big dump. But I think over time, as this sort of growth in our cities carries on, that even that big dump will be used more and more in the building game.
Furthermore, taking a leaf out of your presentation, any sand theoretically can be used for glass making and the other products. But I guess the sought after parts is where the sand is clean. Is that correct?
Yeah, the most critical thing for making glass, Gert, is that the sand has to be extremely clean, and that's the beauty, as I say, of the sand at Philippi that Stephen's going to talk about, and the mining in Australia at Cape, the Cape Flattery mine. That sand, and a lot of it goes back to just geological processes. I mean, if you go and look at the dunes at Macassar Road, I mean, nature has for millions of years been effectively sifting and refining those dumps or those dunes. And of course, you'll understand this, silica being so robust and tough survives, but all the other little particles of, there might have been particles of silica, not silica, but, mica or clay, etc. It's also, those minerals are also lighter than the silica. And they would have been dispersed by the southeaster, which, at times is really extreme. And so nature, has effectively produced that remarkably clean silica, but it's done it over millions of years. We have those deposits, and actually we should look after them a bit more carefully.
John, you mentioned obsidian and volcanic glass, but volcanic glass is not transparent. So what happens with silica in glass making that it becomes transparent?
Well, it becomes transparent, Gert, because again, it is so clean. I mean, obsidian and a lot of these glasses, if you do chemical analyses of them, they still have, a fairly large amount of iron and aluminium and other mineral components, within that glass. And in fact, some of those glasses, part of the reason that they devitrify as well is that they have quite a lot of magnesium, for example. So there's a range of other elements which give you, the different color variations. And it comes back to the fact that ultimately, although that the composition is still, predominantly silica, it doesn't take a lot. And again, that's why, we can produce stained glass. If you think of, these gorgeous glass windows in many churches and cathedrals and that, and the colors that they use, well, glass is very useful in the sense that you can, easily stain it or use an impurity like iron or aluminium or whatever the case may be, and mix it into the raw glass, and it gives you all these wonderful range of colors. So the color and the darkness of obsidian is largely because of the way it crystallized quickly, but also given the range of impurities.
I guess the crystallography and the geometric structure of the crystal lattices must also be a factor.
Yeah, it is, and that's why the big thing in making, successfully making, durable, long-lasting plate glass, and let me just qualify, I'm not the expert on plate glass or float glass, but it's all in the annealing. So it's fascinating if you go into these factories, and maybe one of these days we should get Stephen to arrange that. I think it's, I forget the name here, PG Glass or whoever produce most of our glass in South Africa, have a factory here in Cape Town, and they have these massive baths, and I'm talking massive, like 20 by 10 meters of molten tin. And you then have a furnace at the back end where you melt the silica, and then you pour that silica out across the tin bath, and there's this spread, this thin spread, 2 or 3 meters. They can obviously make it 6 meters or 2 meters, millimeters, not meters, I beg your pardon. So you can make this very thin layer of glass. It lays flat across the bath, and then it's effectively driven or pushed out the other side onto rollers, and there's a whole very carefully controlled cooling process, so that piece of glass anneals in a very systematic fashion, such that you don't have, I guess, this process of devitrification. So if you don't let that glass anneal properly, it almost begins to crystallize, and I presume that then gives, causes weaknesses in those plates. So it looks quite simple, but there's a fairly sophisticated sort of temperature control and the speed at which that piece of glass sort of moves across the tin bath and then out onto, you know, rollers where it anneals is all sort of critically timed.
Fascinating, amazing.
Yeah.
John, do you want to talk quickly about the impact of meteors on sand and silica?
Yeah, Kurt, it's quite interesting that, you know, in various parts of the world, we see meteorite impact structures. You know, the simple one would be the meteor crater in Arizona. On the way, you drive past it and you can go and visit it between, I think it's Albuquerque and Flagstaff, as I can remember, and it's just the most amazing impact structure. Well, interestingly, around that structure, given the impact of a meteor, it wasn't a, you know, particularly big one, but it certainly was a significant one. You actually find impacts, minerals caused by the impact, like cosite, which is a high pressure, I think I'm correct, form of silica, you know, given that impact. I mean, very interestingly, that in the crater of that impact structure, you also find, you know, very fine diamonds, which again would have formed given this enormous, you know, pressure and sudden temperature that the impact caused. I think I'm also correct in saying, and I'm not the expert, but in the Vredefort structure at Vredefort, what's it sort of, well, southwest of Johannesburg, you know, people will probably know the Vredefort structure also shows effects of the impact we see of what looks to have been a very big meteoritic impact. And around there we see, you know, some very interesting structures related to exactly that. So there was a huge burst of energy as this meteorite struck the crust and then threw out lots of rock material and upturned the edges of that crater. So yeah, they're, you know, they're high pressure forms of silica. There's you know, quite an amazing range of different silica types, and that's one of the reasons we've been able to put it to so many applications. It's a very versatile mineral, if I can call it that. And depending how you treat it, depending how you heat it, you know, you can make it into, you know, many different forms. I mean, I always find it quite fascinating to look at, you know, fiber optics, and you have these miles and miles of cable going around the world, and it's actually just finely stretched silica, but extremely pure silica.
Well, of course, the other aspect you haven't touched on is that all of microelectronics depends on silica, because all chips today are made of very pure silica structures, and they have different electrical properties because of the way they are dosed with certain elements that are placed in the silicon. So our whole modern electronic industry and technology is based on silicon.
Yeah. No, well, Kurt, I mean, you know, just to look at this presentation that we're doing at the moment, you know, if it weren't for, like you say, the chips and the glass screen and the touch screens, and you know, if it weren't for silica, well, we probably and fiber, you know, optic fiber, we wouldn't be able to do what we're doing right now. And as you know, I mean, we've had lots of these sessions now where you've got people participating from all over the world, and it's instantaneous. You know, there's no longer really a lag in the communication. It's remarkable.
John, thank you very, very much. It's a fascinating subject, and thank you for your preparation. But also thank you to you personally for the interest you take in spreading knowledge about geology to people around us and making it an accessible science. Thank you very much, and all the best to you.
Thanks, Kurt, and good luck to you and the U3A team. You're doing great work. Keep it up.